Okay, now that we've talked about how to add these all using graphical or tip to tail methods, now we're going to go through the component method of adding these, which is a little more exacting because instead of relying on the precision of my drawings, I'm actually calculating the actual number. All right, so what I did here is I set up the grid that's on your sheet, but I did it large enough so that I can actually include, I wanted to have a sketch of each vector, by the way, not drawn to scale. I want these sketches here so I have something to refer back to when I'm doing my trig. And then I set it up, but I made it bigger so I can actually show my work in each of these grids. Instead of trying to figure it all out in my head or squeezing it in that tiny little space that you had here. All right, so what do I need to do? Basically what I need to do is we're gonna take the Marines approach on this. And the Marines, they break down their recruits and then they build them back up into our soldiers. So we're gonna break these vectors down into pieces and then we're gonna build them back up after that back into our resultant vector. And the way I'm gonna do that is I'm gonna use trig. All right, remember, so, ka, toa. So that's why I want these sketches here, because I want to remind myself that I'm looking for the x component and the y component on each of these. All right, and this is the angle. That's the angle that was given. So that's that 45-degree angle. So I'm going to need that information. So for the x component is along here, and I forgot to include my arrowheads. And again, I like using different colors to make these different components stand out. So I noticed that in this case, the horizontal component of the vector is the adjacent side to the resultant, or to the vector itself, to the hypotenuse. So that means that, let's see, adjacent, so ka toa, I'm going to use cosine for this. So the vector times cosine theta is going to give me the size of that horizontal piece. All right. Now, if you want to double check me on that or see if you're not sure where I got that from, let's just review. Okay, here's my original vector. And if I'm looking for this side of the triangle, this is the adjacent side. Cosine, so ka toa, cosine is equal to adjacent over hypotenuse. In this case, the adjacent side is that x component I'm looking for. The hypotenuse is the original vector itself. So if I rearrange it to solve for that, I see that that is equal to the original vector times the cosine of the angle. So I just wanted you to see that that's where I got that information from. That's how I came up with this equation here. All right? So with that in mind, I need, let's see, cosine of x, or I'm sorry, the x component is going to be equal to the original vector, or the magnitude of the original vector, which in this case is 20 meters, times the cosine of 45 degrees. All right, and when I do that, I'm going to plug that in my calculator. And by the way, make sure your calculator is set to degrees, not radians. So I'm going to take the cosine of 45 times 20, and that gives me 14, and let's see, I'm just going to go to 2 sigs because that's all I was given in either of my numbers there. So that's 14, and in this case we're measuring in meters. All right, so I'm going to need that information for later. And then I'm going to use that exact same approach for each of these. Okay, the x component is equal to the original vector times cosine theta. In this case, the magnitude of the original vector is 25 meters times the cosine of 300 degrees. Okay, cosine 300 times 25 equals, so I get a magnitude of 12.5 meters for that one. And let's see, and by the way, I noticed that in both of these cases, my horizontal component is pointing to the right, which we consider positive in standard XY coordinate system. So far, my magnitudes both have positive values, the magnitude of each of those components. All right, now I'm going to do that last one. Again, the x component is going to be equal to the original vector times the cosine of the angle. In this case, 15 meters times the cosine of 210 degrees equals. So, let's see, what did I say? 15 times the cosine of 210 equals, and I should get a value in the negative direction because if I look at just the x component, that's the direction it's pointed, is in the negative direction. So I get a negative, I'm going to round that off to 13 meters. Okay, so now that I've done that, I'm going to take the exact same approach for the y component, only now, if I take a look, there's my angle, there's the y component, that's on the opposite side, so katoa, opposite side is sine. So now, the y component, the magnitude of the y component is going to equal the original vector times sine of the theta, of the angle. So in this case, 20 meters times sine of, what did I say, 45 degrees, right? Now, this one, I don't even have to go any further. I don't have to go to my calculator because I've got a 45, 45, 90 triangle. I know that both of these components are going to be the same size. So I'm just going to go ahead and cheat. I'm not even going to look at my calculator. I'm going to call that a positive 14 meters. How do I know it's positive? Aside from just what the calculator would show me, is that I can see from my sketch that the y component would be pointing up. So I move on to the next one now. Now, here's my y component. And I see it's pointing down. So right now, I already am primed to expect a negative value for that y component. So let's find out. Y component is equal to the original vector times the sine of the angle, because this time, again, here's the angle I'm given. This is on the opposite side of that angle. And so I end up with 25 meters times 25 meters times the sine of 300 degrees equals, this time I am going to go to the calculator, 25 times 25 times the sine of 300 equals, and lo and behold, it's a negative value, negative 21. I'm going to round that off to 22 because, again, my SIGs don't support too many more digits. So there's my answer for that one. And because of that angle, it makes total sense that this side would be longer than this side. So that's my way of kind of double checking my work. I would expect with an angle like this that the y component is going to be longer than the x component. One more to go. Again, y component is equal to the original angle times the sine theta, the sine of the angle. And this time we've got 15 meters times the sine of 210 degrees. This time, once again, I see that my y component would be pointing down, so I'm expecting a negative value. 15 times the sine of 210 equals, I end up with negative 7.5 meters. All right? And again, I would expect that because with this angle, I would expect this component to be longer than this component. Okay, so now that I've done that, now what do I do? Now what I need to do is, I mentioned we're going to break all these down so we can build them back up. So I'm going to add up all my x components. I'm going to add 14 to 12.5 to negative 13. So I'm going to go ahead and cheat on this one. 14 plus 12.5 plus a negative, so minus 13 is going to give me, so I have a total x component that is equal to 13, a positive 13.5 meters in the x direction. I'm going to do the same thing over on the y. So I add all these up. So I've got 14 plus a negative, in other words, minus 22 minus 7.5 equals. So I get a y component of negative 15.5 meters. All right, so now what do I do with that? Now I know the x component and the y component of what's going to end up being my resultant. So now here's where what I like to do is I like to do a sketch of these. Again, not to scale, but I just want to see what this is going to look like. So you see my x component is going to be, in the positive direction, and it's going to be 13.5 meters long. I see my y component is going to be in the negative direction, and it's going to be just a little bit longer. So what I make that 1, 2, 3, 4, 5. So I'm going to make that 3, 4, 5, just a little bit longer. Again, not to scale, and that is 15.5 meters. And my resultant is going to be drawn from the tip of the first to the tail of the second. So I guess even though I'm not drawing it to scale, I want to make this, since I'm putting this on video for posterity, I'll make that a nice straight line. So how big is my resultant? Well, I noticed that this makes a nifty little right triangle, and so I can use the Pythagorean theorem. A squared plus b squared equals c squared, or in this case, in other words, the magnitude of the resultant squared is equal to the magnitude of the x component squared plus the magnitude of the y component squared. So in other words, the magnitude of the resultant is going to be given by the square root of x squared plus y squared. Plug in my values. All right, so the square root of 13.5 meters quantity squared plus negative 15.5 meters quantity squared. All right. So, let's see, 13.5 squared plus 15.5 squared equals, and then I need to take the square root of that, and I get an answer of, I'm going to say, and I know I'm breaking my rules where I said about sig figs, but that's kind of somewhere there in no man's land, so I'm going to call that 20.6 meters. So the length of my resultant is 20.6 meters. But don't forget, I'm not done, because any vector includes magnitude and direction. So I need the angle. I need the angle at which that resultant lies. So now we're going to use trig again. Only this time, if this is the hypotenuse, there's the adjacent side, there's the opposite side. So katoa, opposite and adjacent together, gives me tangent. So I know that the tangent of any angle is equal to toa, opposite over adjacent. So in this case, the tangent, but what I want is I want this. I don't want the tangent of the angle, I want the angle itself. So the angle is actually going to be equal to the inverse tangent of opposite over adjacent. Well, what are my numbers there? The opposite side, there's the angle. The opposite side is negative 15.5 meters. The adjacent side is 13.5 meters. So I need to take 15.5, let's make that negative 15.5 divided by 13.5 equals, all right, so I need the inverse tangent of negative 29, okay, and that gives me an angle of negative 88 degrees, all right, or if I want that is also the same thing as, if I take that negative 88, I can also take 360 minus that 88 degrees. It gives me an angle of 272 degrees. So my final answer of the resultant after all that is 20.6 meters at 272 degrees. Done. All right, why do we like the component method? Because that vector method went a lot faster. However, because of the inaccuracies in measuring and drawing a scale, that's what I end up with, okay? Here, I get a much better result, all right? So, hope this helps. Feel free to stop, slow down, rewind, whatever you need.